Hello, my name is André Gustavo Carlon, and this is our presentation for the Uncertainties 2020 conference named Stochastic Gradient Descent for Risk Optimization. I will start with a brief introduction, then I will proceed with the problem we intend to solve, the risk optimization problem, then the methods that we use to solve the optimization problem, stochastic gradient methods, and proceed with a numerical example. In engineering, we often need to consider the risk of failure in our engineering processes due to uncertainties. Risk optimization is concerned with the optimization considering these uncertainties in such a way that the costs of failure and the probabilities of failure are explicitly incorporated in the objective function, in opposition to reliability-based design optimization where the reliability constraints are imposed on the design, for example. In risk optimization, the most expensive step is usually the evaluation of the probabilities of failure, usually relying on Monte Carlo sampling. The most common approaches for estimating the probabilities of failure without using Monte Carlo sampling rely on approximating the limit state functions by first or second order polynomials, thus introducing bias on the estimates. Recently, surrogate models like Gauss polynomial expansions have been used to approximate the state limit functions. However, this approach is limited to low-dimensional problems since the cost grows fast with the number of parameters. We propose an approach based on stochastic gradient methods for risk optimization, methods which are known to have cheap iterations and to perform well for both high-dimensional parameter and design spaces. To be able to use stochastic gradient methods, we substitute the true objective function by an upper bound obtained using the Chernoff bound on the probability of failure. Now I will discuss the risk optimization. Well, risk optimization can be understood as the optimization problem of finding the parameters, the design parameters that minimize a function as defined in 2. Here the design parameters are denoted as D and the probability of failure as P for the failure mode I. So the risk optimization problem is such that we minimize an objective function in which we have a weighted sum of the probabilities of failure. To consider the uncertainties, we model them as a random vector x such that each probability of failure is given by the probability of a limit state function dependent on x being positive. So for example, if a failure mode is given by a quantity s exceeding a threshold r, we can write its respective limit state function as in equation 6, as the probability of their ratio exceeding 1. Evaluating this probability of failure can be expensive, possibly requiring Monte Carlo simulation or any approximation. To be able to use stochastic gradient methods, we need an unbiased estimator of the gradient. To get such an estimator, we use the Chernoff inequality on the probabilities of failure, as in equation 7. Then, instead of minimizing the true objective function f, we minimize an upper bound of f hat, here as denoted in equation 8. Okay, so now let's discuss the stochastic gradient methods that we use for risk optimization. So stochastic gradient methods are used to solve stochastic optimization problems, where we want to minimize the expected value of a function. The best known of these methods, and the first one, actually is the stochastic gradient descent method presented in 9 and 10. So each iteration, a single-toe sample of the random vector x is drawn and used to estimate the gradient. Its main feature is that it avoids evaluating the expectation of the gradient using a noisy estimate, using the single-toe sample, of the gradient each iteration instead, given that the estimate is unbiased. So to converge, even with this noisy estimate, the step size here, denoted as alpha k, is reduced with each iteration. Then to minimize the risk optimization problem, we need to introduce this function f such that the expectation of f equals the objective function that we want to minimize, now f hat. So we get f as presented in equation 11. Then we proceed by deriving the unbiased gradient estimator to be used with stochastic optimization, as in equation 13. Note that the second term considers the gradient of the logarithm of the random vector probability density function. However, if the random variables BDFs are independent of the design parameters, this term vanishes. Then for the Chernoff bound to be tight, we need to find the constant t for each failure mode I at iteration k. We need to solve the optimization subproblem in equation 14. This procedure can be expensive, so we developed an heuristic to decide when to update this parameter based on the distance since the last time that we updated it. As optimization progresses, the distance that we use as a threshold to updating the parameters decrease with the square root of the iteration. The same schedule that we use for the decrease of the step size of the step of the stochastic gradient descent. Moreover, we use a running average of the parameters to avoid oscillations and to avoid that the parameters t change too much between iterations. Now I will present the numerical example that we solve. We apply the proposed methods, the stochastic gradient methods and the Chernoff bound and the minimization of the cost of a beam subject to two failure modes, the elastic torsional buckling and the plastic yielding, represented respectively by G1 and G2 in equations 16 and 17. So the design parameters that we want to find are the base and the height of the cross-section of the beam. This problem has been already studied by Tori et al. In the paper of 2019. The true objective function that we want to minimize is presented in 18, where we have the probabilities of failure for the two modes, PF1 and PF2. And we substitute equation 18 by its upper bound in equation 19, where you use the Chernoff bound of the probabilities of failure. Now the random parameters that we consider are the yielding strength Fy, the shear modulus G, the length of the beam L, and the point load at the end of the beam P. Now these four parameters are modeled as truncated Gaussians with mean and standard deviation as presented, and are truncated to strictly positive values to avoid physical inconsistencies. Now here we present the true objective function f on the left with the optimum marked with an x and its upper bound f hat on the right. For this case, the Chernoff constant is tuned for each failure mode for each point used to build the contour, showing that if the constant is well tuned, the bound is tight. We can observe that the two contours look very similar. Now, to minimize f hat, we use a well-known stochastic gradient method, Adam. The results obtained by optimization using Adam are very close to the true optimum used. So the difference in the true objective function and the one found is less than 0.6. The number of gradients that Adam used in optimization is 10 to the 7, or 1.7 million objective function evaluations were used to tune the Chernoff parameter. However, note that if we were to use Monte Carlo simulation with sample average approximation, we would not only bias our optimum estimate, as also we would need much more gradient evaluations to get to the same precision. Now here we present the optimization path in gray with the true minimum marked with an X and the optimum found by Adam with a circle. The starting point is the same as used by Tori et al. We can see that we converge to an optimum that is quite close to the optimum, the true optimum. So, in conclusion, we proposed a new approach for the solution of risk optimization problems, in which we bound the probabilities of failure using the Chernoff bound, and then use Adam, a stochastic gradient method, to find an approximation of the optimum. The methodology was applied to a numerical example using a cantilever beam, validating the performance and low cost of our approach. For further research, we suggest testing other criteria for tuning the Chernoff parameters, testing other stochastic gradient methods, or applying the ideas presented here for problems with larger number of random or design parameters. Now I proceed showing the references that are used on this presentation. And thank you very much for your attention.